Okay, here's a problem we'll work on today. We've been doing a lot of these lately. So again, it's a shear force and bending moment diagram for this structure. This is a little odd. This is not a hinge. This is just a point indicating this is point B. We have a pin connector here at A, and it looks like there is an internal hinge here at B, and we have this element going down to another pin at C. And I want to draw the shear force and bending moment diagram for this whole thing. Okay? Now, what should we do first? Should we get all the reactions first? Probably. So I'm going to start by assuming that I have positive shear here at A. And now it gets a little kind of interesting. Do I come over here and deal with the shear here? Or do I need to take it apart here at B? So let's think about this. At A, how many unknowns do I have in general? 2. How many do I have at C? 2. I cannot find those values with one free body of the whole structure. So I'm going to need to do what? I need to take it apart here at B. Everybody see that? And if I do that, just for a second in your mind, imagine what this section BC would look like. And then consider what the shear force and bending moment in BC would be if all I had was that. If I sum moments at B with no load, what do you think the reactions here are going to be? What does this look like to you? It's a two-force member. So where is the reaction? It's in the line BC. So there's not really two things that we don't know. There's only one. So there is a force right there. And that would be the force, say, at B. So now if you look at it that way, then I can break this apart. Knowing this location, then I can break it down into its components. Since it's in this direction, that means the forces in BC are all axial. There is no shear. There is no bending moment. And that's the key to this particular problem. In two-force members like this, there's no shear. There's no bending moment. So this is just a distraction. It's better to have the distraction now than in the middle of the test, when you look at it and go, what do I do with that? Well, I'm telling you what to do with it. It's a two-force member. So what I'm going to do first is I'm going to slide over here and I'm going to draw a free body diagram of AB, and then on that I will draw my positive shear at A. I do have this force. I drew it backwards here, but I think I'm going to draw it in this direction because that looks more like tension. Right? And let's just say that's a force at B. And then I want to break it down to make my work easier into a Y force and an X force. So that force is actually now going to be the shear at B, right? And down on the right-hand side is actually positive shear. And this force would be the axial force at B, also in the positive direction. Are we concerned about the axial force right now? No. We're drawing a shear force and bending moment diagram. So all I really care about is the shear at A and the shear at B. That distributed load that you see can be resolved into a concentrated equivalent. This has a value of W, just whatever it has to be, and it has a base of 4 meters. So that means I'm going to get a force acting through the centroid of base 8 times height W. So I'm going to have a force of 8W, and that'll be located at 4 meters from either side. Now with this 1 point load equivalent right in the middle of the beam, you can probably guess that my shear forces are both going to be half of that, or 4W, right? Let's go ahead and find out find out what they're going to be. So I'm going to sum moments about B and set it equal to 0. So summing moments about B, the concentrated equivalent force creates positive moment, so that would be 8W is the force, the distance is 4 meters. The shear at A creates what? Positive or negative moment? About B. Negative. That would be the shear at A times 8 meters. And it's not hard to see that the shear at A now is going to be 4W. And then you can sum forces in the y direction for equilibrium. And what will you get? I've got the shear acting up at A, I've got the shear at B acting down, and I've got my 8W load acting down. So the shear at B is what? Negative 4W. So I have everything I need. I have the shear at the beginning of the section and at the end of the section. Yeah.
You don't have to do that force B.
Force B. What was the question?
You don't have to do anything with that.
I don't care about the X component. I mean, once I found the shear at A, I could figure out what B was, and then I could find the axial component, and then I could also find my reaction over here. But don't care about axial force. We're not drawing an axial force diagram. So now, what's the moment at A? 0. What's the moment at B? 0. So I know my end conditions for both shear and bending moment. So I think I'll redraw this so it won't be so small. So here's just the section of the beam from A to B. I've got my uniform distributed load, which has a value of W. On this side, I have a positive shear equal to 4W, and on this side I have a negative shear equal to 4W. And also this distance, I left the distance off, 8 meters. So from that I can draw my template. There's the left side and right side of my beam. It doesn't look like I need any kind of internal point, because you'll see that it's a continuous load. There's no point loads. There's no discontinuity in the applied load. So right now I'll just leave it like that. I'll go ahead and define my positive x-axis and my positive axis for shear. There's no units given with W, but since everything's in meters, I'll just assume these units will be kilonewton. And now I'm ready to start. I'm going to start from my left side and go right. What's the shear at the beginning? 4W. So I'll write 4W. What's the shear on the right side? What kind of shear is that? Positive or negative? That's negative, right? So that's negative 4W. And we know from our previous work that the change in shear between any 2 points is just the area under the load diagram. So what is the area under the load diagram from 0 to 8? It's a rectangle, base times height, 8W. And it's positive or negative? Negative. So if you start at 4W and you subtract 8W, you get negative 4W. So that looks good. The slope of the diagram, or the derivative, is equal to the load. And what is the load everywhere? It's constant and negative. So I have a constant negative slope. So there's my shear diagram. Now we do generate a new point that's interesting to us. That's this guy right here, and that's a point where the shear goes from positive to negative and passes through 0. What's interesting about that point? Yeah, that's going to be a place where the moment curve has a 0 slope, which probably means it's a max or a min. So that would be a good point. How do we find this distance, x1? Well, we can apply the same thing. So what's the change in moment? What's the change in moment? Shear. I'm sorry. Change in shear from 0 to x1. We start at 4W and we go to 0. So that change is minus 4W. Right? What is the area under that part of the curve? So if I were to project that line up, this is the area under the curve, loading curve, that I'm looking for. And what is that area? Yeah, it's a distance of x1 and a height of w. Is it positive or negative? It's negative load, right? So this will be negative for x1. Oh, I'm sorry, negative wx1. Sorry. Right? Base x1 times height. That's the area. And this change is minus 4. So I just have to set those two things together. So I got negative 4w is equal to x1. So what's x1? 4. Which means it's happening right in the middle. If that's 4, then this is 4.
Assuming just assume it's 4.
Assuming is not a good thing to do.
Distributed load outside forces.
I can make a small change to that and it wouldn't be in the middle.
Well, yeah, if you change it the way it is.
Now I could just move one of these reactions in a little bit.
Simply just looking at that like that, you can pretty much tell. Just
my advice to you, if you get it right, then it works. If you get it wrong, then it doesn't work. So I always like to explicitly show what I'm thinking in something like that, and it does support your theory. And it's not a good. It's a good theory, but it doesn't mean it works every time. This works every time. Question? So now I have everything I need to do. Let's draw the moment diagram. So I'll again assume positive x. I'll assume a positive value for moment, and I'll also assume kilonewton meters for my unit. We talked previously about, we know the moment at A, it's 0, external pin. And at a hinge, we know the moment 0, so there we go there. I've got those two things. And now I have the relationship that the change in moment is the area under the shear diagram. So what is the area under the shear diagram for this first section? Well, that's pretty easy. It's a triangle. So 1/2 base 4 times height 4w. You get what, 8w? 8w, right? And that's positive. So I go from 0 plus 8w, I get 8w. And the slope of the moment diagram, which is the derivative, is equal to the shear. So let's see, what's the shear value at A? It's positive 4, so I'll draw a positive slope, and the value decreases to 0, so I'll draw a 0 slope. So that helps me kind of qualitatively know that my quadratic curve has that kind of shape. And now when I go from 4 meters to 8 meters, the change in moment here is given by this area under the curve. And you can see it's the same value, except this area is negative. So if I have 8W and I subtract 8W, I do get to 0. And of course then the slope is equal to the shear. In this case, the shear starts off at 0 slope, and gets larger and ends up being a negative slope. So we started out with a positive slope, ended up with a negative slope. And then you can sketch that in. My graph may not look it, but that's a symmetric parabola. So what's the maximum moment in the beam? 8W, and it occurs in the center. What's the maximum shear in the beam?
4W.
Yeah, and it occurs at either A or B. Remember, sign is not an indication of value, it's just direction. You know, in the 3rd grade they teach you that -4 is way smaller than +4 on the number line. But in engineering, that ain't the way it works. The magnitude's what's important, the sign usually just means direction. And if you were to use, say, Excel, you have to be careful about that. If this were -5 and this were +4, and you'd used Excel and asked for the minimum value, it would tell you it's -5. And it's really not. That's really the maximum value. So you've got to be careful. That happens occasionally. So, any other questions about this problem? I think the reason it's a pretty simple problem once you get past that distraction. Yeah. I like that, distraction.